Hi, good afternoon, everyone. Uh, that was a pretty technical slide from my colleague Alfred. I'm afraid mine is gonna be the same. So, quick introduction about myself. My name is Varun. I am based in Bangalore, India, R&D office, and I support isolation product line as an apps engineer. And today we are gonna talk about uh, the journey that TI has gone through in terms of isolation and in terms of providing isolation solution and our latest offering for the Opto-emulator portfolio. Okay. Uh, so before I start, can I know how many of from the audience have ever used isolation in their design or any? Okay, I see that. All right. So we have one. So without wasting time, I'll start. So introduction, um, basically I'll start when to use isolation, what is isolation, and why is it critical in today's, uh, you know, highly electrical environment. So in basic, uh, uh, in basic terminology, isolation is nothing but you are transferring data from one device to other device, and you want the unwanted DC and the AC transients to be blocked in between, so that your other device doesn't get damaged or your signal integrity doesn't go for a toss. Okay, so that is what is meant by isolation. When to isolate into the system or the application that you're using? Number one is basic human safety. For example, consider uh, a patient sitting in an ICU, or you driving your car with using USB and suddenly lightning strikes. So the human safety needs to be of utmost importance in those applications. So the first one, sorry. So the first one here is blocking the low voltage system, high voltage system, and the human interface system. The second is the ground potential difference. This particular scenario occurs in two remotely sitting nodes which are communicating with each other. Let's say we are talking about hundreds of meters or tens of meters, and in these kind of applications, there can be a potential difference between the ground reference of node 1 and node 2. This causes a ground potential difference and a ground loop, which then reflects into your signal lines, and your signal integrity goes for a toss, especially in high-speed environment. The third one here mentions high-side components. So any one of you who has ever used a H-bridge for a motor drive operation, you know the high-side switches sitting on high-side IGBT sitting on the upper two portions of the H-bridge needs to be isolated with the digital signals that's driving them, because your ground of the digital domain and high side domain will be shorted, and the operation will go for a null. So there we have we again need to offer isolation between those two signals, so that the digital driving device the signal from digital driving device doesn't go for a compromise. And the last one is high voltage EMI transients. This is similar to what I said. For example, consider lightning strike or EFT noise, electrical fast transient noise from the motor drive system, and ESD strikes. So I'll showcase these in more detail in upcoming slides. And why now this is of utmost importance is because we are seeing our move towards solar inverter technology. I mean, and motor drives for supporting higher and higher factory automation. For high-speed communication over long distances, as I said, RS-485 is one classic example, where you communicate through multi-node system, and they are switching in Mbps speed. So to break the ground loop here, you need to use an isolation device. And third one is again related to electric mobility, where you have a high voltage battery system and you as a driver using your interface in the driving seat. Moving forward. So this is a pictorial representation of what I just said. The circuit one here resembles any low voltage system, an MCU system or a human interface system. And this is a high voltage system which can be your field side in the factory or any lightning prone circuit or a moving ground circuit. So this isolation, first of all, it blocks the high voltage noise and protects the low voltage domain and the human safety here. The second is where it's more interesting is about the ground loop. Now this is the long distance multi-node communication that I was talking. When you have a ground potential difference between two nodes, this results in your signal integrity on the signal line, and and the way the isolator helps here is the ground potential difference still exists, but the isolator that we are using and that TI provides needs to be robust enough to handle that disturbance between two ground nodes, which is spec'd in many terms as common mode transient immunity. I'll talk about more later. So this is one showcase of the application. The third one is on the high voltage EMI transients. Now all the external world interfaces generally has a protection diode between the field domain and your device interface. Now the reason this is still not enough is there lies a disconnect between the device ground and your protected earth ground. So what you're seeing here is RHV, CHV kind of resembles the isolation between the device ground and the protected earth ground, but this requires a whole lot of design complexity, and the ratings, the standards that the international body requires cannot be guaranteed in this one. This is where our isolation solution comes into picture, where let's say if you have a lightning strike on the bus, the whole stress goes through the TVS diode to the ground, and then this isolators handles the transient behavior between the ground, the protected earth, and the ground to node, where the protection is maintained as well as the data integrity, the signal integrity is also maintained through the isolation. So this is a MCU domain and this is the field side domain. Yeah. Okay. Few isolation terminology. Is my voice audible? Sorry. So few isolation terminology here. How to select basically the best isolation device for your application if you are choosing one. Okay. So the first one is which kind of isolation is best for you. There are 3 isolation ratings that is popular in the market, which is functional isolation, basic isolation, and reinforced isolation. The supplementary isolation and double isolation is other terminology that are mentioned in the standards that define these terminology. So the functional isolation is nothing but you have the correct operation between two ground domains, but without a requirement of protection against electrical shock. Basic isolation is you have the signal transmission from two ground domains, but it offers one basic level degree of electric shock. The supplementary isolation is not a category of the isolation device, it's rather a additional parallel device that the standard talks about, but the combining basic and supplementary isolation gives you double isolation as per the standard. A supplementary isolation component under basic isolation gives you a double isolation. And reinforced isolation, which is the highest rating of any isolation device, is basically two basic isolations in series. So they have the highest level of voltage ratings that I'm going to talk about in next slide, and has high lifetime reliability, highest lifetime reliability. Now, these are the terminology which is mentioned in the standard. When I say standard, there are two major international standard bodies that regulate these numbers. It's IEC and VDE working together for the European markets, and UL 1577 for the US markets. Now, VIOTM and VISO is nothing but maximum transient peak voltage and maximum withstand isolation voltage. These two, VISO is under UL, VIOTM is nothing but under VDE. Both of them basically demonstrates how good is the isolation barrier against a temporary high voltage phenomena, which is why these are always rated for 60 seconds. And whereas maximum repetitive isolation voltage and maximum working isolation voltage, these are the long-term stress for the lifetime of the device that is mentioned in the data sheets. If you open an isolation data sheet, all these specs are always mentioned there. And coming to the reinforced isolation, none of these parameters drives the reinforced versus basic. It's rather the V surge or VIOSM if you open the data sheet of any isolator. A 10 kV, a standard 1.2 microsecond, 50 microsecond surge waveform, but a minimum of 10 kV pass level is required to claim a reinforced isolation. This is the only spec that defines the reinforced isolation. Creepage clearance, I'll talk more in the coming slide. It's nothing but the distance between side 1, side 2 via air and the package. And CMTI is the common mode transient immunity between ground 1, ground 2, where one side is considered cold side and one side is considered hot side. So quickly glancing over the creepage distance and clearance distance. So the distance from lead 1 to lead 2, basically side 1 to side 2, through the surface parameter is creepage, whereas through air is clearance. The reason why this is important is this also directs and defines, plays a major role in your basic versus reinforced isolation. Although it is not defined by any standard, but it brings the basic manufacturability concern. So if you want to have a reinforced isolation, you need to have a minimum creepage. That comes from the high voltage rules, physics rule. So going forward, this is a small animation that I have over on CMTI. The right hand side is what I say protected earth, which is solid ground referenced signal. And this is your disturbed environment. For example, your high H bridge switch or ground loop disturbance domain. So the way this, if you see now the CMTI is always spec'd in kilovolt per microsecond. And typically our digital isolators are spec'd for 100 kV per microsecond. It's always about the slew rate with a maximum VCM, how much common mode voltage, DC common mode voltage you can apply across side 1, side 2, whereas maintaining a slew rate and the communication chain doesn't break. Excuse me. Now coming to the TI's isolation technology that we have today. Now this journey has been 20 years of R&D, quality, reliability testing, along with new product development in parallel. So I want you to see this slide here. Currently, few years back, we had only capacitive isolation technology, which is our reinforced isolation tech, homegrown in TI. And over the time, in parallel, we have also developed the transformer-based or inductive isolation. Now, both the isolation technology utilizes the silicon dioxide-based dielectric, which offers highest dielectric strength, which means you can have lowest DTI, which is distance through isolation, creepage clearance, but still have the highest isolation ratings. And yeah, this is a pictorial representation of the difference between a capacitive and the transformer-based isolation tech. So the capacitive-based isolation tech, if you see, this used to be a 2-die MCM. When I say MCM, it is a multi-chip module. None of the isolation device is ever going to be a single chip module. It's always going to be a double chip minimum. So the ISO cap or the dielectric sits in both the left die and right die, where if one of the, let's say, die gets or isolation gets damaged, your one die is always going to be damaged forever. Now, with the transformer technology, what we have achieved is we have been able to isolate or bring out the isolation die out of the communication dies. Earlier, it used to be a part of the communication die. So this is the difference. If you see, this lightning here defines where the high voltage technology is residing inside the multi-chip module. This is a quick comparison for both. Since TI heavily invested in the capacitor isotech from early 2000s, we have matured this technology, and today we have a 1.5 kV RMS, which is your working voltage. And this, almost all the isolators that we have today have this rating of reinforced isolation. And 1 kV is minimum needed for reinforced. So the ISOSAX, because of its small size and lower DTI compared to, if you see the distance between the high voltage caps, it also defines your high voltage rating. So here, this right now we have achieved 1 kV RMS for the transformer technology, and it's a work in progress to come here. EMC, when I say EMC, mostly radiated emission, radiated immunity, the CMTI, the conducted emissions. It has been, with the new transformer-based technology, we are seeing very promising results in EMC for emissions immunity, where we have passing results for CISPA 32 with almost noise floor from 30 megahertz to 1 gigahertz. And same goes for the immunity, where we pass 30 volts per meter without any sweat. The DTI, which means the distance between high voltage caps, and here the inductor coil 1 and coil 2 is 17 micrometer. So yeah. Now coming to the portfolio that we have to offer to our customers. So column 1, column 2, column 3 shows your generic purpose isolators. It includes of functional isolators, the digital isolators, which is the most common used isolation component in the isolation applications. Then, excuse me, ultra low power isolators. These are nothing but a little low on speed, but it saves enormous amount of power between each communication cycles. So the total power consumption is very low here. The analog and digital optometers I'm going to talk in more detail in coming slide. Apart from this, we have isolated interfaces, which is a combination of our isolation tech along with the most commonly used in bus protocols in industrial and automotive, which is ISO RS-485, CAN, and I2C. The digital inputs portfolio is nothing but your PLC domain application, where you have the field side digital inputs coming from the high voltage prone areas to the control room, where you have digital MCU based. Basically, it converts 24 volt inputs to 5 volt domain. And we have one device to offer in ISO LVDS. It's a high speed differential part. And ISO USB has been our latest release in 2022, which is compliant to USB 2.0 with high speed compliance. Yeah. And the last one here is isolated DC-DC, which is, so there also we have a split, small split. One is the digital isolators in the device with a transformer driver. Transformer driver is used to drive the external transformers in case our signal isolators with integrated power don't suffice the load requirements of the customer in on secondary side. So generally these devices can provide load currents of around 120, 130 milliamps. But if you have a higher requirement than that, then you need to use a secondary transformer outside the device, which can suffice your load requirement. Okay. So whatever I said just now, it's the device. These are the device part number and families. The digital isolators have these top parts, hero products from isolation, where I'm going to focus on 6.4 and 6.5 for today. And optoemulators, we have 3 family of devices, which is unique in its own way. All 3 are different purpose optoemulators. And these are the part numbers for the isolated interfaces and the ISO-Watt series. The isolated DC-DC is called ISO-Watt from TI. Where one thing I would like to mention is this, the ISO-Watts of TI offers best-in-class EMC performance for any DC-DC integrated part. It passes CISPA 32 with noise floor. That is a flex that we have. Now coming to the digital isolators. So from left to right, what it describes is the working isolation voltage, which I mentioned 1 kV RMS, 1.5 kV RMS. So this particular device, ISO 65XX, is the first functional isolator from TI, and it's the industry's smallest footprint digital isolator with a 3x2 mm DFN package, leadless package, with 200 volt RMS working voltage, and it offers a CMTI immunity of 150 kV per microsecond typically, and a minimum of 100 kV per microsecond. This is a great option for people who, or the customers or the applications who don't require a electrical shock prevention. If you want to just break the ground loop, this is the part to go. Now coming to the mid portion, or the last portion, I would say, the ISO 78XX. This is a pretty older generation part, but it still is the highest isolation rated part from TI, where your isolation working voltage is 2 kV with a UL rating of 5.7 kV RMS. And this is the only part from TI which has DWW offering in our portfolio right now, which is wide body package with a 14.5 mm of creepage clearance. Coming to the general purpose isolators, I already talked a little about 70XX, which is our which is offered only in basic isolation because of the narrow body package. But the if you see the currents here, the power consumption that I was talking about, it has 0.13 milliamps per channel at 1 Mbps. This is generally used in industrial application for 4 to 20 milliamp sensor applications. And our latest and most hot release in the market is the ISO 64XX family. So this is the first general purpose digital isolator with ISO SAX technology, the ISO transformer technology, which is the most cost competitive part in isolation for digital isolators that we are offering. And it passes all the sections with flying colors in terms of its operation, in terms of, operational voltage, in terms of the speed. Currently, the samples are available which are 100 Mbps compliant, but when we finally release the part by 2Q end or 3Q beginning, this is going to be 150 Mbps. And a CMTI of typical 150 kV per microsecond with best-in-class EMC performance from 30 megahertz to 1 gigahertz of noise floor performance, and a 30 volts per meter of radiated immunity, and a 150 volt per meter automotive radiated immunity. So, yeah. I talked about the creepage clearance, and this is, I want you to read this slide by, so the top row explains the reinforced isolation, what and all packages we support with reinforced isolation. Again, reminding the reinforced isolation is only determined by the V surge, which is minimum of 10 kV across barrier that the device needs to sustain. And in the same packages, DW and DBQ, we have, and 8D cannot be supported for reinforced because of the package constraints, but we have basic isolation ratings for DW and DBQ. Of course, there's a difference of price because this is certified and qualified for those highly stringent high voltage ratings. But again, someone needing basic isolation can use the same functionality of the device, but with the lower cost. Now, the reason I wanted to show you this is the size difference in the functional isolation. The 6.5 series that I just talked about has the 3x2 mm leadless package, and this has been getting very good attraction from the market, and this was released last year. And the same package, the same device is offered in a 8D package with for someone who needs a narrow, a wide body. This will offer a higher working voltage. That's it. Okay. 16DW has been the best-selling isolation package for throughout the year from TI. And the same thing, if you convert to 8 pin, it's called 8DWV. And with narrower pitch, it's DBQ, sorry. Okay. All right. Now, yeah, a little bit more detail on the 64XX because I wanted to highlight the improvements and the typical application diagram here. So 6441 basically means we have 4 channels, out of which 3 are forward, 1 is reverse. So as I said, the typical here is, the typical CMTI is 100 kV per microsecond. The operational voltage, VISO rating from UL is 5 kV RMS. It's qualified for both reinforced and basic isolation. Working voltage of 1 kV RMS, since it's a SAX single standalone transformer technology. And the data rate, the electrical benefits that you have is the voltage range of 2.25 to 5.5 with 2.5 milliamp of current per channel at 1 Mbps. Um, the one more advantage of it is the propagation delay improvement from our previous offerings of devices. A 6.2 nanosecond prop delay and 7 nanosecond at 5 and 3 volt corner. One more feature that has been missing from our devices earlier is high and low, over voltage tolerant inputs. What it means is, if you're having a, for example, this side one, you want to switch off the power supply in middle of the operation to save power, but you don't want to configure these input channels. This used to be a violation of absolute maximum ratings from datasheet in our previous devices. So everything needed to be shut down. Let's say if you have a complicated MCU which is getting used for some other application in parallel. So, and you are also using the same power line for the isolator and this one. So if you switch off this supply, now with over voltage tolerant inputs, you can have the 5 volt or 3 volt or whatever voltage domain that you're operating in at these pins. So earlier it used to be a violation for absolute maximum, and the device used to get damaged. The internal ESD structures or diode structures were not made for that. But with this device, from the feedback that we have got from the customers and the field, we have implemented that feature in this device, and it's absolutely working fine. The package that we'll be offering on 6.4 is DW, of course, 16W with 8 millimeter creepage, DBQ, 8 pin for the 2-channel variants, and 8D variant for basic isolation for the 2-channel variants. The application for the digital isolators are like wide. A typical application that you see here is nothing but a SPI, isolated SPI transmission over 2 different domains. So that's why 3 forward channel, 1 reverse channel is so popular in this kind of applications. And yeah, everything else is covered. Coming to the functional isolators, that is the industry's smallest footprint isolator that is there, and it has a 200 volt RMS working voltage, which is sufficient for breaking the ground loop, but not enough for the but technology itself is not sufficient to block any electrical shock. Now, even with the small package, with the tri-temp, this is a tri-temp operational device, and it has, since it is a lower package, size package, the power is consumed also very less, 1.9 milliamps per channel. And yeah, I think, yeah, VCM, of course, when you reduce the working voltage, the VCM also comes down. Generally, we have 2 kV, 3 kV VCM for our reinforced isolators, but the common mode voltage, basically DC voltage that you can apply between side 1 and side 2. Okay. Now, I wanted to talk distinctively on our optoemulators. So, anyone who has used or designed a power converter might have used analog opto feedback in their design. But if someone has done that, maybe you know what is the pain with those designs. So the story behind optos are basically, these were designed and manufactured way early from 1970s. And when I say opto, I mean photo, because they use light-based transmission with light-based transmission across barrier, with the dielectric medium in between being air or epoxy or some polyamide most of the time, which can never give you a reinforced or a basic isolation rating of as reliable as a silicon dioxide. Excuse me. the reason we call it as opto emulators is because it emulates the diode behavior of the an optocoupler, but it doesn't have a LED inside. It is purely based out of our silicon dioxide based isolation tech. And as I said, we have 3 offerings for the opto emulator portfolio. First one being 81 ISO M81 series, which is the analog opto, I would say, because here you give a certain X amount of input current and you get a Y amount of output current, as long as the output I mean the side 2 here is able to supply that current. So there is a constant relation between IF, the forward input current, and the collector input current, which is nothing but CTR. It's called current transfer ratio. Now the challenge with existing optocouplers is that first of all, they have a lot of variation in CTI that I'll talk in more detail afterwards. And the whether be it analog or digital or a opto relays or opto MOS switch, the main problem is the aging effect of the input LED that is used in optocouplers. So due to that, the customers had to design with a higher input forward bias current, whereas which increases the total power consumption of the system. Typically 8 milliamps, 9 milliamps is what the optocouplers are designed for the longer duration and longer lifetime duration, whereas this is not the case with TI's opto emulators. If we guarantee minimum current of 2 milliamps, it's for lifetime. You can operate that device at 2 milliamps for lifetime. Due to the small package, this cannot be offered in reinforced, whereas it is offered for 3.75 kV RMS, which is nothing but your basic isolation. And we have the offerings with part-to-part replacement for optocouplers, which is 5-pin, 4-pin narrow body package. I'll explain about the more details in upcoming slide. Yeah, it's nothing but whatever I had talked right now. Pin-to-pin alternative to optocouplers, so you can just drop in replacement in your existing design, and you can see the advantage here. The power consumption gets reduced significantly because of the lower IF input forward current guarantee over lifetime. The CMTI is something that you won't find in data sheets for optocouplers, but we have it over 150 kV per microsecond for our 8.7. 8.7, okay, I'll come to that. It has 25 Mbps of operational speed for an opto, single channel opto. The CTR, as I said, we have a very flat CTR response across the operating current. Generally, if you see optocoupler, the CTR variation throughout IF changes vigorously, more than 100% variation, whereas we have it under control, tri-temp, between 100 to 150%. When I say 150%, I mean if your X input forward current is X and Y is your drawn output current, then Y by X is your IC by IF is CTR. Okay. Just to understand the structural difference between a traditional optocoupler and highly reliable offering from TI on opto emulators. So as I said, these are highly prone to aging effects, and due to this, these are generally not preferred in automotive and space grade applications. And the dielectrics, as I said, the mold compounds, the epoxy, and these are the least offering dielectric strengths in the industry. And the optocouplers, since they don't have an electrical transmission, they require a different level of certification, which is the IEC certification, but it is different from the electrical optoemulators. But this does not require a lifetime testing for them. Whereas we go through the VDE 80844-17 for the lifetime testing. That is where that reliability and non-aging effect comes into picture. And of course, the dielectric strength is again coming from the silicon dioxide. Excuse me. Okay. So coming to the three devices that I talked about earlier. The first release in our optoemulator family was back in 2023 with ISOM 87 series, which is nothing but a digital optoemulator. You give one, you get one, and it has CMOS output and an open collector output. The data rate supported by this is 25 Mbps. You have the VCC. VCC is because this is a 5-pin configuration, and you need a secondary supply to support the high-speed operation here. And the prop delay is well within 15 nanoseconds, which is again best in class, and it is reliable over lifetime for tri-temp operation. And these are some of the part-to-part replacement devices, which if you compare the data sheet and the specs, you will find the difference here, what we are talking about. Yeah. Now coming to the 8.1 series, ISOM 8.1. This is the analog feedback, analog behavior optoemulator. So the isolation ratings remain same between the 8.7, 8.1 because the package is same. Only one pin gets added on the secondary side, so that is not a problem. The creepage offered here is 5 mm. Now, this particular device has a CTR spec for this and the competition devices that we have. CTR is nothing but your relation between input current and output current. This, since we have multiple CTR offerings, the standard device, which is 8110, it varies only between 100 and 150%. And this is guaranteed for lifetime, which does not require over designing and added complexity in the system when you use this part over the traditional optocouplers. Okay. Also the I think the bandwidth, the bandwidth over this channel, the basically between 4 and 3, is close to 680 kilohertz, which is again because you have a load resistor here to limit the current. So the channel is quite respondent to the input and output changes. Okay. This is the family of devices that I was talking about, 110, and this we also offer in bidirectional. So if you have an AC input, this bidirectional part can also be used. This is a DC input, this is a AC input. Your current here will remain same. The bandwidth is -3 dB. Yeah, it's larger, 6 times larger than the traditional optocouplers here. The last one in the latest release in the optoemulator last year was 8.6, ISOM 8.6 series. This is nothing but a replacement for opto relays. Especially in test and measurement applications, you would have seen a lot of relays being used to switch signals from one port to another. This particular device has a 4 DFG offering in terms of package, which is way much smaller than a traditional optocoupler. The cost is way too competitive when it comes to the same footprint offerings from the photocouplers, high reliability photocouplers. There are some which offers that, and some of the money specs to look for in this devices is the switching, the leakage parasitic, the current leakage, and your bandwidth. How fast of a signal you can transfer from pin 4 to pin 3. So all of here, this device performs in par with the competitors, and for example, the leakage here at room temp is less than 100 nanoamps, and across temperature it is 250 nanoamps, because at hot you see higher leakage through FETs. The turn on and turn off time for a typical load is way too symmetric compared to the optocouplers, and it's 200 microsecond, which is enough for these kind of applications. Once the device is on, how fast of a signal can go through this? Because once the device is on, this channel is conductive. So that bandwidth is close to 950 megahertz. So 950 megahertz of a signal can be passed through this channel. And C off. Basically, so whenever you use this kind of devices, generally these are multi-node connections. So you have same line going through, touching different nodes of these devices. So the off-state parasitic capacitance becomes important in high-speed applications. So there we have a typical C off of around 14 puff, 14 picofarad, where yeah. So this puts us in lead when it comes to the solid state relay or the opto relays market space. So after this, I have some of the content and collateral to showcase how and why opto emulators, how each of the offerings from the opto emulator, or which is either digital, analog, or your opto switch, is advantageous in all of your sockets where the traditional optocoupler is getting used. So yeah, that's it from my side. Any questions?
Can you back to slide 22? Okay.
Yeah.
So the DFN 3x2, this is ISO device also, right? So how many die that you assemble in this packaging? I mean the low side die and high side die also, right? Or the single silicon?
Sorry, I didn't hear. I was not able to hear you.
How many silicon that you put in the 3x2? Two, right?
It's a capacitive based.
Okay,
yeah.
okay, thanks. And then can you back to slide 15? Sorry, go back again. Go to previous slide. Okay.
This one or?
Yeah, this is the one. So this is a new technology that TI developed for the ISO device, right? I think what I hear, that's the previous one you have two silicon, right? And then you add another silicon. This is I think
3.
Yeah, the middle silicon. This is like a transformer.
Yes, this is the isolation die, which gives high voltage protection. Whereas these two are the communication dies.
I see.
Yes.
But why the ISO capacity is lower than the previous one? Previous one, the existing one is 1.5 kV, but the new.
That is a limitation of the way the transformer is designed by our process technology team right now.
Okay. But that is a silicon also.
But it is still reinforced. Yeah.
Silicon also, right? This is.
Yes. The patterning is different. So it might look that it is same, but the cap distance, and since you have two of them in series, it offers, and the distance also increases, right? Because of the lead frame in between.
Okay.
So this is a more, I would say, robust and matured technology. This has been developed over past 20 years. This is a development of past 6 to 7 years. So we are working towards increasing this in par with this, but today also it has a capability of reinforced isolation rating.
But the advantage of the new technology is for what?
Okay, that is a very good question. The advantage of the new one is, so if you know the series capacitive signal chain, first thing is it improves in our design flow cycle. So you have a earlier what used to happen is you design a new part and you have to take care of this isolation component to be embedded inside the communication die that you are designing for.
Okay.
Now this design and this design is become independent of this. You only need to bond the two dies from each side to the isolation, and the HV high voltage protection, high voltage ratings are taken care by this, and of course the lead frame. The lead frame is also designed for that.
Yeah.
But this for every device you need not go through the high voltage qualification reliability, or that goes for months and less.
Okay.
Second is the it helps us to reduce the cost of the overall solution, because this might look two die, but the high voltage constraints here inside the die makes it more costly than designing a two smaller dies and having one isolation die separately. Only here the cost that increases here is the two bond wires
Okay.
from each side. And since you know the series capacitive, the signal to noise ratio from side 1 to side 2 transferring in this system requires more power to be injected to be detected on the right hand side, which is the RX side. Whereas the coupling factor is what I'm basically trying to say is coupling factor. You have to understand the way isolation, basically we had two kinds of isolation data transmission methodology. One is called on-off keying and one is edge based. But in both of the scenario, you have a high frequency component that gets injected from TX to RX to be read by the RX. A lot of the signal strength is lost through the two series cap to be detected by the RX or the receiver side die. Whereas here, the coupling factor improves by 10 times, and this requires less power requirement on the left hand and right side die for it to be operational on a day-to-day application.
Okay. Thanks.
Okay, I have one question. I already used the one of the transformer technology of isolation, but I want to know what is the new form of transformer technology. Another band already used, you already know what I mean with the band. So you have any advantage that I should change to this model, transformer one? Yes, another band already used it.
First is cost, straightforward.
It's cheaper? Okay.
Yes, it's cheaper.
Okay. I will try consider
It's
about the
cheaper
spec
and
and price. Okay.
Yes, it's cheaper.
I have already used one, but I'm not sure this
Which
one
one?
is a
Which
new
is the
one.
device that you are using, if I may ask?
You already know only one transformer, another brand in the
Okay.
market. You have only two brands.
Okay. Second is improved EMC performance on this one. The radiated immunity performance on this is very promising on the transformer based. And since the signal to noise ratio is higher in this transformer based, your CMTI immunity, the common mode transient immunity, because of gets better in transformers technology, because again the signal strength gets reduced on the RX side, and this is more susceptible to, although we have it in par, but this is capable of doing much better. That's it. Thank you.